Miss Howard's chemistry class, Heat and Thermochemistry, Unit 10, Part 7. And it seems there is a difference between hypothesis and guesstimate. Alright, Roman numeral number 5 on your notes, exothermic and endothermic processes. Again, we've already hit these words before, so these should be familiar to you. All chemical reactions, all changes in physical state, they will either involve an increase in temperature or a decrease in temperature. That means they're either going to involve a release of heat, exothermic, or an absorption of heat, endothermic. One of those two things is going to happen. Always, always, always. Now, sometimes it's enough that we could actually feel it with our hands, but you know, your skin isn't the best way to find a temperature change. You really need to use a thermometer. There are tools for those things. So capital letter B, exothermic. Another word, and you may see it on the tax test or the chemistry EOC, is exergonic. So that EXE or EXO means it's giving it off. Exergonic, exothermic. This means that the system's going to lose energy. It gives it off. Exo, out. It gives it out. It loses systems to the surroundings. It loses energy to the surrounding around it. The heat flows out of the system. It's losing energy, so we have negative delta H, or the enthalpy, the change in heat, is going to be negative. The surroundings get hotter, but the stuff we're looking at, like the chemical reaction or the phase change, that's actually getting cooler. So it gives away the energy, so it's going to have a negative delta H. In a physical change, an example of an exothermic reaction would be, okay, it looks like I've kind of swapped these around, so I'll have to fix those later on. In a physical situation, it says melting and evaporating are endothermic, and that's true, but I really should have exothermic, like freezing is going to be exothermic. It's got to give away the heat. So I'm going to go ahead and read and go with what's on the list here, because I think that'll match up with your notes. But melting and evaporation are endothermic. In order to melt the substance, it must take in or absorb heat. Breaking things apart requires energy, so that's, again, endothermic. So apparently I just kind of got off my list here and kind of combined the exo and the endo on here. I'll fix that in class and go over it a little bit. Exothermic reactions would be reactions that give off heat, like combustion. You set something on fire, it's going to give off some heat to the surroundings. These always cause the temperature of the surroundings to rise. Combustion is an exothermic reaction. It's a great example of that exothermic reaction. So when you have an exothermic reaction, the energy is in the system, and it actually releases the energy to the environment. So that energy is going to move out from the system into the surroundings. So the system releases or loses energy to the environment. Isn't that just a spiffy animation? Okay, capital letter C, endothermic. Endothermic is also, another word for that is endergonic. This is when the system absorbs energy from the surroundings. It's going to suck in the heat. It's going to take in that heat, and so it's taking in energy, so it's going to have a positive enthalpy or positive delta H. It's increasing the energy. The surroundings lose the energy. The energy is taken from the surroundings and put into the system that we're looking at. Physical freezing and condensing are exothermic, so it looks like number 4 on each one of the last one and this one. It looks like I kind of swapped my number 4s on there, so I'll try and fix that. So physical freezing and condensing are exothermic. So in order to get the liquid to change into a solid, you've got to release the heat. So this number 4 really should go with the exothermic, and the other number 4 should go with the endothermic. So you might want to make a little note on that, make a little marking on your notes for that. So forming connections, forming bonds, actually makes things more stable, and so it actually gives off heat to the surroundings. Chemical equations, chemical reactions that are endothermic, these are the ones that are going to feel, if it changes enough in temperature, they're going to feel cold to the touch when they do this. They absorb the energy from the surroundings, and they cause the surrounding temperature to fall, so it feels a little bit more cold to us. Now, again, it has to be, significant enough for us to tell the difference. The products are higher in energy than the reactants because they're absorbing energy from their surroundings. They're sucking it in, so they've got more energy inside of them. Usually, if it's an endothermic reaction, the products generally aren't quite as stable as the reactants were. So endothermic reactions don't happen. They're not nearly as common as the exothermic reactions are. The products absorb the energy and they absorb the heat. Alright, so here we have the endothermic. It's the system that's going to absorb the energy from the surroundings. So here we have the surroundings and energy's going into the system. So it's sucking the heat into it, so we have a positive delta H. Energy is increasing for this stuff. Alright, so chemistry happens in, whoa, what happened here? Chemistry happens in moles. I'm going to backtrack one and see if I can get it to stay on there. I'm not quite sure. An equation that includes energy is called a thermochemical equation. Alright, a thermochemical equation. So you look at the equation, we took methane, CH4, we added oxygen to it, so we have a combustion reaction, and we always get carbon dioxide and water that forms. But you'll notice it's got plus 802.2 kilojoules. We can measure it in joules or kilojoules, whichever we feel like. So what they're saying is, hey, when you burn this gas, it's going to give off energy. How much energy is it going to give off? 802.2 kilojoules. So it's an exothermic reaction. It's going to warm up the environment around it. 1 mole, now if you look at the balanced chemical equation, there's a 1. There should be a 1 in front of that CH4, but remember, we don't have to write the 1s. 1 mole of CH4 is ultimately going to produce that 802.2 kilojoules. So when you make 802.2 kilojoules of energy, you're also going to make 2 moles of water and 1 mole of carbon dioxide gas. So that energy can be included into your balanced chemical equation. You don't have to memorize how much energy is associated with it, but just recognize that, yeah, you can include that in your balanced chemical equation. Oh, now I'm going backwards. What's going on here? There we go. Oh, and here is my lovely cartoon for you guys. I like that one.